Alright, today we're going to take a look at some of the gas laws that we've gone over the last couple of days. These are going to include Boyle's Law, which we'll start with on this PowerPoint slide, Charles' Law, and Gay-Lussac's Law, which came due to Charles and Gay-Lussac's today, Monday. So if you've been gone, this is perfect for you. So we have Boyle's Law. Basically, what I like to remember with Boyle's Law is that it's an inverse relationship, and there's a teacher here at PV with the last name Boyles as well. And so Boyles is an inverse relationship between volume and pressure. So we see that the volume of a gas varies inversely, in other words, opposite with pressure. So if one goes up, the other goes up, down. You have to remember though, temperature and the amount of gas are going to be constant during this entire time. So we're only going to change volume and pressure. And look at how, if you change one, what happens to the other. There's our equation right here. P1 V1 equals P2 V2. Very easy equation right here at the bottom. If you will know three of these and you'll have to solve for the other just through algebra. We're going to go through one example here out of the PowerPoint, and you can just view the other one on your own time. If you have questions, of course, just stop up and ask. Here's our graph between pressure and volume. Typically, you're going to be changing pressure and watching what happens to volume. That's why pressure's on the x-axis. All inverse graphs do that sort of motion there, that downward to the right motion. Alright, our first practice problem. A tank contains a volume of 3 liters, so volume of 3 liters. There is our V1, okay? And a pressure of 4 atmospheres. So if we read that, that's the animation. Turned out the way I thought it was going to, but that's okay. So we have pressure first. That pressure is 4 atmospheres. The second volume is 3 liters. It's asking us what is the final volume if we lower the pressure to what atmosphere. Now, if pressure in this case is going down, we should expect volume then to go up, all right, based off of a relationship of it being opposites of each other. So we should expect an answer higher than 3 liters. All right, so we're going to substitute into our equation, which is going to look exactly as you see here in the middle of the screen. 4 times 3 is 12, divided by 1 is 12 liters. Atmospheres cancels out here, so we can scribble out atmospheres, scribble out, and so we're left with liters. All right, that's Boyle's Law. That's about as easy as it gets. One thing that you do need to do, however, that you can't forget about, because that's going to come back here in a day or so, is that pressure's unit has to be in atmospheres. Okay, convert it into atmospheres if it's not given to you in atmospheres. Volume is going to be in liters. If it's not there, if it's given to you in milliliters, simply divide your number by 1,000 to get you to liters. Here's another problem where if you read the question, you have 50 atmospheres of pressure, volume of 3 liters, pressure is 20 atmospheres, so what's the final volume, just as before. Substitute in 50 times 3 divided by 20, and you should get 7.5. All right, that's Boyle's Law. Very straightforward, an inverse relationship between pressure and volume. Charles' Law, I like to think of it to help me remember the equation, and the variables that are with Charles' Law is that Charles had direct TV. All right, if you have direct TV, you probably really get that. So we're looking at the relationship between temperature and volume here. Volume is going to be directly related to temperature. If you heat something up, a container up, its volume is going to expand. That's just what happens. All right, so mathematically, that's the equation right there in your lower right corner. All direct relationships have that graph. There you go. The main thing that you have to remember with Charles' Law is that your temperatures have to be in Kelvin. If they're not, then you need to get them there, and I'll show you how to do that here with this question. A tank contains a volume of 3 liters, so there's our first volume. All right. Some people like to, like I did, write it here on the side, or you can just do this. So I've had students in the past, they circle this and they'll label that volume 1. There's nothing wrong with that either. And a temperature of 100 degrees Celsius. Now, at the top of this page, it says you have to convert that to Kelvin. Well, that's a very easy conversion to do. Getting Celsius to Kelvin, degrees Celsius to Kelvin, all you do is you add 273. So you see here, 100 degrees Celsius is just 373 Kelvin. We don't know our final volume. That's what it's asking us to find in the second sentence. and we're doubling our temperature from 100 degrees Celsius to 200 degrees Celsius. All right, so 200 degrees Celsius is just 473 K. You need to be sure that you substitute in that number and that one instead of the Celsius numbers. All right, so it's going to go into that equation, as you see here, and to solve this equation out, all you're going to do is cross multiply. So you're going to do 3 times 473, 3 times that, 373 times our second volume. All right, that's going to look like that without it all solved out for you. And then you're going to divide both sides by 373. All right, just using basic algebra here, 373. And that gets your second volume by itself, 4 liters. We should expect that to happen. Our temperature went up, our volume went up. So there we go. Here's another problem, 275 liters, 293 K, 313 substituted in. All right, again, just as before, in order to solve out this answer, cross multiply, and solve out for your second volume. So this side, you'll divide both sides by 293, and you get 294 liters, and it goes up as it should because your temperature goes up. And our final gas law is going to be Gay-Lussac's law, which is looking at pressure and temperature. As he says there in his little thought bubble here, your tires will heat up when you go driving along the road, especially in the summertime, and so the pressure will go up in your tires as they heat up. All right, there's a couple of demos on the website you can watch as well. This equation should look very similar to Charles' law, and it does, except now we have pressure, so you need to be paying attention to the units of atmospheres here. All right, but you solve it exactly the same way, so there's no difference here. You're still going to do cross multiply here to solve out your to get to your variable, your unknown. Okay. Temperatures need to be in Kelvin. All right, so we have a pressure of 3 atmospheres, a temperature of 100 degrees Celsius. Again, we have to get that to Kelvin. So you see here in the PowerPoint, I have it saying that, adding 273 to get us to 373 K. What's our final pressure if we double the temperature? All right, so our temperature goes up. According to Gay-Lussac's law, our pressure should go up as well. So let's see if it does. We just substitute in, just like we did with Charles' law. So we cross multiply to solve for P2 in this case. 3 times 473 divided by 373, and you get 4 atmospheres. And I should have said this before, but you do not solve this out by doing 3. You don't do 3 divided by 373 and then do something magical over here. Just cross multiply. It's an extra step. It's not a big deal, so just be sure you do that. You can do reciprocals too. If you don't know how to do that, then just cross multiply. And then one more, and then that'll be it for this video. Find the pressure needed if you wanted to put gas at 50 degrees Celsius and 75 atmospheres. So those two numbers are together, okay, these two values, 50 degrees Celsius and 75 atmospheres. So that's going to be our first pressure and our first temperature. All right, as you see here on the PowerPoint, temperature is converted to Kelvin for you. You want to put it into a vessel that's at 65 degrees Celsius. Now, what pressure is that? And this is really important because if you need to put a bunch of air or something into a new vessel, you have to take into account where you're going to store it. So if it's going to be in a hotter storage room, you want to be sure that this new vessel, whatever it's going to be, can withstand whatever pressure it's going to have when you raise that temperature up. All right, substitute it in as before. Okay, substitute in correctly. 75 times 338, 323 times P2, and you should get 78 atmospheres. I went through these pretty quick, which isn't that big of a deal. I mean, pick up a calculator, try to calculate these out along with the video. You can rewind back, you can pause to be sure that you're getting this right. If you're having trouble seeing why is it at 370, you know, the temperatures are in Kelvin, or you're not sure if you're calculating this things correctly, stop me before or after class or even during class, and I'd be happy to help you out. Those are the 3 gas laws.